My name is Mariano Zero, and in this video I'm going to show you how to use Splines of Chebyshev using the mocax library. So let's take a look at this example that I have here. So mainly we want to identify which are the situations where you would like to use Splines of Chebyshev. The first situation is where you have a singularity in the function that you want to approximate. So I've cooked up this function here that I've called func singularity. The reason is that it has singularity. I would like to show you exactly how it looks. So we run this. So this is what we have. So the domain is going to be between -10 and 10. The first part of the function is a sine function, and when it gets to the value of pi, then it becomes a logarithmic function. Of course, it's not just a logarithm because I've displaced it in such a way that the whole function is continuous. But what we have is a function that has a point, in this case is pi, where you have a singularity, that is, the function is not differentiable at that point, but that in the remaining part of the domain, it behaves really well. In fact, it's analytic on both sides. And we know that the condition of being analytic is very important if we want to use Chebyshev. So it works perfectly well, with the exception of that point that can cause all sorts of problems. In fact, let's say that we want to build, just to show you an example, a mocax object that has no idea whatsoever that there's a discontinuity, or in this case, a singularity in the domain of the function. We basically first build the mocax object, ignoring the singularity, then evaluate it in its domain, and we want to compare it to the original function. What will we get? We get this approximation, which is pretty bad. So in order to avoid this kind of situation, what we tell the initializer of the mocax object is that we want to split the domain into two parts, exactly the parts where the function behaves well, but we need to tell it where to split the domain, and that's where the parameter special point in the initializer of the mocax class comes in handy. So let's take a look at the documentation. We want to check the mocax class, the initializer of that class, and we see that the parameter special point, which comes with a default value of none, is the one that controls these points. So in this particular case, when I have a singularity and I know where the singularity is, which is, by the way, a case that we would normally face in finance, because functions or pricing functions, despite being analytic, sometimes have singularity points or points of discontinuity, like they would have on payment dates or barriers, for example. So what we do is pass the parameter special point that needs to be an object also defined within the library of type mocax special points. So if you go back to the documentation, you'll find that class mocax special points, and you can check initializer and all the methods that it has. So what we do is specify this list here with all the singularities that it may have in the domain. In this case, we have a one-dimensional function, so we write it this way. So it's a list of collections of points. Each collection of points would be the special points, or the points where we think there's going to be a singularity or a discontinuity along that dimension. Given that we only have one dimension, we only have one collection of points, and it only consists of the point at pi, or the point pi. So we pass this list to the constructor of mocax special points. That gives us this variable that we've called mcx spec points, and we pass that to the initializer of the mocax object. And by doing that, we've specified the mocax object that we want the splitting to be done at that point. Of course, this is something that you could do yourselves. You could build as many mocax objects as you want for a particular function, but then it becomes a bit of a hassle to deal with all of them and know exactly, if I want to evaluate a point of the domain of the whole function, which of the objects has to evaluate it, and so on. So the library provides that ability. You don't have to worry about it. You just build the mocax object by specifying which are the special points, then call the eval method, forget about which of the sub mocax objects has to be called to then evaluate the point in question. So the building of the object is very, very simple. It is essentially the same as we've been doing so far. So we run that bit. This is the first part of the building. The second part of the building is that, and then we evaluate the function on the points, or the mocax object on the points that we're interested in. What I want to do now is compare the original function that has that point of inflection, or that singularity, with a mocax object that we've built by specifying a special point. And if you compare it to what we had before, which was awful approximation, now we have a much better approximation. In fact, notice that, and we can improve this, and we can have more control over it in the following way. Notice that I've passed here a single n value, even though we know that the domain has been split into two. And we know that the mocax object, if you take a look at the description that we've printed, says that you have two n values, one of 7 and one of 4, even though you passed a single value of 10. So if you pass a single value of n, the algorithm inside the library will decide how to split that n into the objects that it has to create by splitting the domain. But you could specify, I want this value of n for that object and this other value of n for the second object. And you do it in this way. You can put 10, 4. So you have to be careful to specify as many values of n as sub-mocax objects the splitting will create. So if we run the whole thing again, now we have an object with a value of n equal to 10 and a value of n equal to 4 for the other sub-mocax object. And we see the accuracy that we obtain here, which is pretty good. So this is the way that you would normally deal with singularity points. But what happens if we've got a discontinuity? I've got this function that I've also artificially created with a jump. I want you to see how that function looks like. And it's this function over here. Essentially, you've got the same as before, the sine function, and at pi, instead of having a logarithmic function starting from that point, we've got a jump down of several values, and then the logarithmic function. So you've got a discontinuity there. So how do we deal with this particular problem? The way that you do it is by isolating the singularity. And one way which is very convenient is if the discontinuity, sorry. If the discontinuity takes place at pi, take a point very close to pi but just below, and another point very close to pi but just above. So take pi minus 10 to the minus 6, and another special point at pi plus 10 to the minus 6. So you've introduced that discontinuity two special points. Then you pass to the constructor or the initializer of mocax special points, and that gives you your special points, and then you can pass to the initializer of the mocax class. Also notice that we've got the choice of passing a single value of n, but then the algorithm will decide how to split it in all the sub-mocax objects, which in our case are 3, because we've got two special points. Or you can specify an n per sub-mocax object. So let's first go with one single n. But before we do anything, and as you would expect, I don't want to pass any special points. Who do you see the result? And the result is just, I need to uncomment what the mocax object would do on the plot. So run that again, and you get this really poor approximation as a result of that point of discontinuity, which is messing things up. But if we include the special points, what we obtain is much better approximation. And you see here, at construction, the n that you passed of 10 has been split into 7, 1, and 4. 1 makes sense to put a 1 there because the interval, which is in the middle, is tiny. So it doesn't need that many Chebyshev points. But you could have also specified 10, 1, and let's say 7. If that's what you wanted in each of those intervals. Run it again. And now you've got even better approximation. And this is where you have more control over what are the n values that correspond to each of the sub-MOCAX objects. And finally, I want to give you another situation where you could use special points even when you don't have singularity points in the function or a discontinuity. So let's go back to our old friend Black-Scholes. What we've got here, let's change the domain so that it makes sense. We can't take negative values. Let's say 50 to, let's say 250, something like that. Let's even make it wider, because the situation that I want to obtain, in fact, I'm going to change something. I'm going to make this Black-Scholes function a bit difficult to approximate. So let's say that is close to maturity, which I've fixed here. By the way, the parameters that I've passed are strike 100, interest rate 2%, sigma 20%. So I've got this function, and let's say that I pass a single value of a single n value of 10, and I want to approximate this function, which we know is analytic. In principle, you wouldn't need special points. So all good. And we see what happens. And we obtain, I mean, reasonable degree of accuracy, but still we know that this can do way better. And in fact, it does if you increase the n value. Let's say that you go a bit aggressive and you go all the way up to 60. And boom, you've completely resolved it. You've got an accuracy of 10 to the minus 4, which is pretty good. Now, we know that this value of n is particularly high in this case because of the way that the function behaves around the strike. So one thing that you could do is isolate the strike and pretend in some respects that is like a singularity point. In fact, it is close to being a singularity point because we know that in the limit, when Black-Scholes, the pricing function matures, you end up with a singularity point at the strike. So what we do is we consider special points around the strike, let's say 85 and 125. So basically what this does is split the domain into 3 chunks. The chunk below 85, and then the other one between 85 and 125, which is where most of the change of the function takes place. And then 125 onwards. And then what we do is try and be a bit more intelligent about the choice events. So we pass a value, let's say, of 10 in the first one, 30 in the second one, and 10 in the last one. And run it by asking the constructor or the initializer to consider special points. What happens in this case? We obtain exactly the same level of accuracy, but notice that instead of passing 60 points in the Chebyshev mesh, you passed 10, 13, and 10. So almost half of the points that you originally needed. And in this way, you save quite a bit of time in the construction phase of the object. So this is another way in which you can use it. So just to wrap things up, in this video, what we've seen is that the library provides the option, or gives you the option, of easily handling the breaking up of the domain of a function, where you want to break the function up so that you can make the whole building and evaluation of a MOCAX object more efficient, either because if there's a singularity point or a discontinuity, you're not going to get good approximation, and hence by specifying these points as special, you will get really good accuracy, or because you want to make the building of a MOCAX object more efficient. And in any case, there's just extra functionality. You don't need to use it necessarily, but if you want to use it, it can improve quite a bit some of the already quite impressive results that you're getting. Thank you very much.